All right, so I don't actually want to make it super formal, so you guys just interject whenever you want. I don't care. Ask questions. I have extra slides, so I can always fill time or not. The other thing I want to say before I do anything is that Ian Wallen's presentation in 2 weeks.
I'm 2 weeks.
3? Okay, so 3 weeks. So he's doing non-equilibrium statistical mechanics. So that's also really broad, but it also it really is a prerequisite in some sense for mesoscale simulations. So I'm not going to steal all of his thunder, but I will just say a few things. And if we get lost, stop me and we'll just poke around. Okay. So I think the first obvious question is, what is mesoscale? So that's the first thing I typed into Google just to make sure I knew what I was talking about. So we'll start with one of these nice diagrams of spatial scales versus temporal scales, and just kind of fill it in gradually. So this is all rough. So if we're modeling or we're talking about quantum mechanical systems, we're talking about scales on the order of an atom and very short time scales. And this is, I think, an electron density map from DFT of, I think it's a buckyball, C60. So, just going to loosely say we're modeling the behavior of electrons and nucleons. That's protons and neutrons. And if we want to go up a step further in scales, we can talk about classical mechanics and the approach molecular mechanics to modeling. And you get some more range of spatial and temporal scales. So maybe we can extend this to milliseconds even, depending on the simulation and the machine. But we're kind of restricted in how big we can make the simulation. So I extended this beyond micrometers, but that's probably not going to happen if you're doing atomic resolution. So molecular mechanics includes atomic resolution stuff and blobs that are coarse-grained things. So we can talk about that too. So this is stuff that's on the order of molecules, let's say, and they could be big. Now I'm skipping this here because you guys know where I'm going to go with it. But at the largest scales, and this actually can just go way beyond meters. I mean, we can talk about entire planets. But continuum mechanics covers fluids and solid mechanics, and it's at a spatial scale where we can treat the matter in a smooth way through some kind of averaging. So this is some kind of combustion simulation going on. I think that's the hypothetical Aurora spy plane with some shocks around it and flow fields. This is hard to see. This was supposed to be modeling mosh pits. I don't know if some of you guys have seen that paper, but you can model blobs of people or lots of people as like a continuum. You can do that with traffic. Okay, so mesoscale is somewhere in here, presumably. So I just have cell division. This is a cell pulling apart, and these are some mitotic spindle. It's really hard to see all the chromosome detail, but anyways. So this is on the order of a cell size. But then you could have other things that are not like cells, where you have these fluid instabilities that can be exacerbated by fluctuations that start to take place when you move below millimeters towards microns. So this is pretty simple. This is like really detailed and complex. These are both kind of in the mesoscale, I guess. And this is a kinesin walking on a microtubule and pulling along a vesicle. So these things obviously look very different. I could have put a ton more stuff in there, but the whole point is that this is pretty vague. So I kind of just ballooned it outwards, and we'll see if we can talk about molecular mechanics, continuum mechanics, and how they kind of overlap and can deal with mesoscale phenomena. So I guess I leave a question mark here. What are we actually modeling? Oh, I should say that when we're doing continuum mechanics, we're mapping quantities to a grid. So you can imagine that if you have particles, then you might have particles and you might also have grids. It could be a hybrid, but you could also have other conceptual ideas. So I'll leave it as a question mark. All right, so I'm going to just actually leave all of this up here because I don't want to go through it in detail. It's just to give an idea of all these kinds of systems that might be classified as mesoscale systems. So, enzymes, we saw an enzyme in the previous slide. Bacterial flagella and cilia and all these other things that wiggle around to make cells move. Molecular motors, polymer melts, so that's huge in chemical engineering and whatnot. Colloidal solutions, does everyone know what that is? So just so if you have suspended particles in any kind of solution, so you could be talking about sedimentation for river flows, or maybe you have a particular kind of lubricating material, but it has suspended particles. So this makes these types of systems hard to model because you can't treat it as just a simple fluid. I guess that falls under that category too. Active matter, there's this kind of active matter or active fluctuations paradigm. So it's talking about, let's say soft matter, where at an even smaller scale there's some input of energy. And that energy kind of flows up to larger scales, and then you get some kind of order, spatial order. So that's like flocking of bacteria. And, you can even have kinesin motors, moving in together, maybe even in lockstep almost. Who knows? And the why is, I guess, kind of obvious, but I think the main thing, or the thing I like to think about in terms of justification, is can we actually understand how information is flowing at the nanoscale well enough to even harness it? So I don't, engineering applications are interesting, but I think, once you're able to do this, then it kind of says something pretty deep about what's going on. Are there any just questions? I can pause here for a second. Just mouth this dry.
What exactly is meant by the statement nanoscale information flow?
Just literally information moving between different spatial regions, say, on the nanoscale. I mean, it could be, microns, but submicrons, being vague. Is that satisfactory?
Yeah.
Okay. All right. So, to attack this very broad problem, I'm going to start bottom up. So we're going to start looking at a molecular system. I guess some of you have seen this, but maybe this is a good point of contact. So if we're talking about so-called large-scale conformational changes of an enzyme, so this is an enzyme with these two mobile domains that are colored, and it basically binds some substrates, kind of locks them into place. They undergo some chemical reaction that's accelerated because they're optimally positioned, and then it lets it go. So this cycles between these states, and that could take anywhere. So for a generic enzyme, could take anywhere between microseconds to way beyond milliseconds, I guess. Should go in a second. Okay. So enzymes aren't the only things, proteins, that can undergo large structural changes. So this is just a depiction of a membrane transporter protein in a lipid bilayer. And they basically move stuff across the cell membrane. And they have some input of energy that allows them to undergo these motions and do the transport. But again, large-scale motions. And you have some kind of complication here where you might think you need to model the environment, because this is not just water, say, surrounding an enzyme. You have something else. So in thinking about modeling these systems, you have to think about what kinds of phenomena you are interested in and how long it takes physically for them to happen. And so, like I said, it's microseconds basically and beyond for a lot of these. The issue, if it stops freezing, here we go. The issue is that we have to take very, very small time steps. And I can get into the reasons why that is later, but the short answer is when you have bonds between atoms, you have to, in order to model their oscillations in a stable way, you have to actually take time steps that are sufficiently small that it can capture the oscillations without the system blowing up. So you can't let the atom get too far away. So you have to kind of capture multiple frames during an oscillation. So basically, order of femtoseconds for time steps means we have to take a huge number of time steps in order to observe the phenomena we're interested in. And by the way, this could be the order of time for one thing to happen, one cycle, but if we want to even see this many times, then it's an even worse problem. So explosive solvent simulations are expensive, all atom simulations. So to just really drive this point home, in classical mechanics we have basically Newton's second law right here, and just the velocity, of course. I'll get back into Hamilton's equations as it's relevant. But so basically we're integrating these equations forward in time, and in order to do a simulation, you need to know what system you're talking about, and that's defined through this potential U. So in the case of simulation in, say, water and it's some protein, we would probably have this split between non-bonded and bonded interactions if we're capturing atomic detail. And I guess all the details don't matter that much, but you can just see there are electrostatic interactions. These are all covalent bond type interactions, distances, angles. This is Leonard-Jones potential capturing basically hard spheres, roughly speaking, so things don't collide. But then there's this van der Waals attraction, so you can capture stickiness. Okay, so the point is we have a lot of terms, but this makes things a pain because if you guys know, the energy landscape picture, and of course our energy is defined by this entire thing. Then when we explore different states of the system, then we can think about the system being at different points in some space, and at each point there's a certain amount of energy associated with it, which we just evaluate the potential. So of course, then we have this problem where if we want to sample something interesting, say we move from this state A to B, where these are two low energy regions, well, the problem is we're going to be stuck just statistically. And so these low energy regions are overly sampled, even though we're interested perhaps in all the interesting things that are happening in between. Okay, so, whoops. Okay, so one thing to just bear in mind is that the sampling cost is proportional to, so basically the computational cost per time step times however many steps you need. And this computational cost basically depends on how expensive it is to evaluate the potential. And if we're talking about exploring different states of the system, well then the bumpier the landscape, well, then the slower we explore. And if you increase the number of atoms in your system, then this obviously goes up because you have more force evaluations. But so does this if you go down to, say, the atomic scale. So let's say you're just modeling blobs, and each blob represents a carbon and some hydrogens. Well, if you want to actually resolve the carbon and the hydrogens rather than just the blob, well, now you have 3 extra points that you have to keep track of. And that extra detail creates roughness that slows down sampling. So in order to get around this problem, there are these so-called enhanced sampling methods that I'm not going to go over, although they're related to mesoscale and hybrid methods in some sense. Maybe one I will point out are these implicit solvent models. I think on the next slide, I should have one of the problems I just want to highlight. So a problem with macromolecular simulation in particular is that the dimensions of the solute pretty much dictates how much water you need around to serve as a buffer, loosely speaking. So in order to, I guess I'm missing a slide somewhere. So in order to simulate the system, you have to simulate, of course, all of the solvent, but then it gets quite expensive. You can see that if you want to model this transition between this closed state and this kind of extended state, well, then you probably can't have just this amount of water, because if it later then transitions to this extended state, you need enough water to accommodate the transition. Otherwise, this will stick out of the box. Okay, we'll come back to this, actually, this diagram. Any questions? Okay, so this gets kind of mathy, but you guys can just stop me, or if you look sufficiently bored, I'll try to go through it. All right, so let's talk about what kind of modeling we're doing with molecular dynamics and then try to work our way up. All right, so we have Hamilton's equations of motion. So positions advanced by dh/dp, and we advance, so the acceleration basically depends on how the Hamiltonian changes with respect to positions, which is basically your potential energy. There we go. Now, I want to just make a connection with the Liouville equation. What happened?
No kinetic energy in the Hamiltonian?
I took it out. All right, so I should say this. And if we're not talking about, say, magnetism, we don't have a Lorentz force, well, then we don't really need to care about how the energy, we don't have a potential energy or some kind of force that depends on the velocities. And so this really just is the kinetic energy. Well, okay, is that good enough?
Yeah, if you want to do the left thing, then, and you don't have kinetic energy in your Hamiltonian, then this ends up being 0.
Oh, yeah, no, I see what you're saying. And so let's pretend I included the extra kinetic energy term. Okay. Oops. Oh, that was right. Okay, so I just want to talk about these equations in general, make a connection to statistical mechanics, and then we'll see how, I guess I'll say the Liouville equation might have fingers in all the methods I'm going to talk about. So if we treat these Q's and P's as 3 n-dimensional vectors, so we have n particles in 3D space, then we can talk about the phase space distribution for all the particles in the system. So if we want to talk about how this distribution changes in time, then we can take a, say, total time derivative and write this equation. So this is just time rate of change of the density, phase space density, plus, so this is a 6 n-dimensional divergence here, divergence of the flux of rho. So what I mean by flux is, I don't know if I'm on the board here. You see me on this side. So what I mean by flux is, so let's say we have a bigger grid. We have some grid, and it extends off out in these other directions. And in each grid cell, we can talk about the amount of stuff in it. In this case, it's just the amount of points, so which is just representing our system, right? So if I'm talking about the flux of stuff, or the flux of phase space density, I'm talking about systems moving in and out of some region of space. And so this is some region of phase space, so let's call that Q. Call that P. Flux of stuff really is just stuff moving across these boundaries into or out of it. So this then is a statement that whatever goes into the cell here is the only thing that's responsible for changing rho. Okay, so it's just it's a statement of conservation of stuff. Okay, so what I wrote here is that the flux is rho times its velocity. So if the velocity, in other words, how fast these coordinates here are changing, if that's larger, well then there's stuff moving across the boundary faster, and so the thing will change faster. And if rho, of course, is larger, well then for any given amount of rate of flow in here, well, if you double rho, well then you double the amount of stuff that's transported into or out of the cell. Okay, so if I plug this in here, if I plug this in here, and then I write it out in terms of Q's and P's, I get this equation. But then, of course, I can say, well, what if my system, the Hamiltonian system, I can define some Hamiltonian. Well, then I can insert the expressions from up here into my equation. And then there's some math, blah, 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 cross terms that cancel out. But you end up with an equation that tells you how the phase space density changes in terms of your Hamiltonian. Okay, so I'm just doing this kind of substitution here. This is a dumb substitution. There are extra terms that end up canceling out. Okay, the point is, though, that this looks like this is not supposed to be there. This expression basically is telling us that everything here is responsible for what's changing our phase space density. So you might want to ask, well, actually, I think I come across the question in a second. Yeah, okay, so let's get rid of this again. I don't know why that's there. Is that confusing to anyone? All right, so the key point is that the fact that this is equal to this for A 0 means that our phase space density is conserved, which means our phase space, you could think of it as, is not compressible. And this is basically equivalent to what we say in statistical mechanics, that all these states in phase space have equal a priori probabilities. And then you can think of more general things. So like, what if we're keeping our system at constant temperature, the canonical ensemble, so as opposed to keeping total energy fixed, then you get a distribution that's now Boltzmann distributed.
What does the term a priori mean?
Well, you can take it as basically a postulate.
No, but what does the term mean? Equal a priori probabilities.
The probability of any state is assumed to be equal. Any point in phase space is the same weight.
Okay.
Yeah, so microcanonical ensemble. All right, so I'm not going into the stat mech because it would take too much time. I just wanted to point out that if you have a Hamiltonian and then you're using some kind of numerical method to integrate these equations forward in time, then you can connect to statistical mechanics. Okay. So my question is, what if phase space is compressible? So ignoring this 0, what if this is not equal to this? And so just leave that in your mind, and then I'll just come back to it, and I'll ask one of you maybe to answer it. All right. So now I want to draw a comparison between the Liouville equation and Boltzmann transport equation. So they should look pretty similar. I'm writing this f as a kind of distribution function, and I'll get into it more in a second. This is supposed to come first. If I rewrite this equation now, again, these zeros are annoying, sorry about that. Notice that these are almost analogous. So this q dot is like a velocity, and this p dot is almost like an acceleration. Okay, so this rho, however, depends on 6n variables. This f is actually the single particle distribution function. Okay, so in order to get from here to here, you have to have some way of getting rid of all the other variables. So one thing you might think of is, well, let's just average over the n minus 1 other particles, all their positions and momenta, do some kind of integration, and then we might be left with something like this. And that is actually one way you can get the Boltzmann equation. Why would one do that? Well, maybe it seemed to be beneficial to do that averaging because your system is homogeneous enough. And then you don't actually have to deal with integrating all these variables individually. So you have a much smaller number of degrees of freedom. All right. This acceleration, I should point out, is due to any forces that are possibly in the system. So one popular way of rewriting this is to split the acceleration up into something due to an external force, and accelerations caused by collisions. And I've written this in this way because this just means the rate at which the single particle distribution, F1, changes due to collisions. And now I'm writing with a 1. Okay. Is that all okay for now?
1 for one body?
1 for, yep. Yeah, so what I should have written here, I'll just write over here. F1 is P or V. So it's 6-dimensional. Okay. Now, if we say have pairwise forces defined between any two given particles in the system, we can express the collision integral as basically an integral over a two-body distribution function. And this because the forces depend on the relative locations of two particles. So let's say we plug that into our equation, and I'll explain what this means in a second. We get something on the left-hand side that's pretty much exactly what I had here. But then on the right-hand side, I have an explicit form for the collision integral. All right, so this, in principle, is capturing all the ways in which our single particle distribution function will change because things are basically colliding and they're scattered. Right? So if nothing is scattered, well, then you just keep going the direction you're going up to maybe some external force. But if we didn't have an external force, then you just keep going. However, you will, if you're obviously scattering stuff in some region of space, well, then you can change the number of things that are there, and the density will change. Okay, so it turns out, and I won't prove this, maybe Ian will do it. Turns out that the Liouville equation can be represented by a hierarchy of equations. So you do a decomposition into n equations, where the first equation is this equation that looks like the Boltzmann equation, with some collision integral, depending on F2. And then it goes all the way down to the n-body distribution, which depends on all the stuff, which depends on well, n plus 1 distribution. Okay, so let me rephrase this. Let's say n is equal to 2. Well, then it depends on the 3-body distribution. And so you extend it all the way to n particles for your system. And all these equations together are equivalent to the Liouville equation. So the Boltzmann equation can be viewed as a truncation of this entire hierarchy, where you've kind of neglected these higher order correlations or higher order interactions. And, no? Is that okay? All right, so BBGKY stands for Bogoliubov, Born, Green, Kirkwood, and Yvonne. Something like that. Okay. All right, anyways. So that's just, it offers another way to look at what's actually going on. I should say that what's commonly done is to treat all, so say I'm talking about the 10-body distribution. It's common to treat that distribution as a sum over pairwise interactions. In principle, though, everything in your system can depend on simultaneously on 3 or more positions and so on. So those would be many-body interactions. Okay. So Boltzmann equation, what do you do with it? You just try to approximate this. That's basically what all methods do. And this contains all of the interactions in our system that we're pretty much interested in. Plus, I guess this if you have an external force. Mm-hmm.
Does this assume that you have a homogeneous system where you just have one type of particles?
No. Yeah, I mean, you can subscript F and include whatever other stuff you want, and of course they'd be coupled somehow.
So then you have many different two-body densities, for instance.
Yeah, and I imagine it gets pretty complicated. Okay. All right. So the last thing I want to connect to is hydrodynamics. So if you start with the Boltzmann transport equation, we're talking about basically removing the specific identity of every single particle and just talking about where we expect a single particle to be. So if you take this equation and take what are called the statistical velocity limits, and so you basically integrate over all the range of velocities, minus infinity to infinity. And if you want to take the nth moment, then you take the product of v to the n times your single particle distribution function. So if n equals 0, for instance, then we're just integrating over all the velocities in our single particle distribution. And so that means that we can get all the things that are at a given point in space, because we've considered all the different particles, whatever velocity they might have. And so that gives you a continuity equation for mass. And you can do the same for momentum and energy. I should note that this is really a tensor product, so it would really be, VV, and you would get something here that's tensorial. But under certain conditions, you can reduce the set of equations to only 5. So scalar, scalar, and vector, and you get the scalar energy equation by contracting over that tensor. It's kind of involved to see why that's the case. Mm-hmm.
What are the rules for the number of bodies that you put in the moment integral? Because I know that as you go, because it's not just integrating over the one-body distribution function. Eventually you're doing integrals of the 2 bodies, and eventually you're doing integrals of the 3 bodies. Right?
Yeah, I guess I'm not.
What's the rationale for what point do you have to go past the one-body distribution function and calculate the next moment?
Well, so I mean, first of all, this right here is an integral over the two-body distribution, right? So you can actually go through an analysis where you assume that pairwise collisions are the only significant thing that are happening collision-wise. So like if you have a dilute gas, right, then the chances of seeing a three-body collision is tiny compared to two bodies, just circumstantially. So then you can talk about conservation of momentum and energy going into a scattering event and coming out. And if you do that integral, well, then you end up deriving a stress tensor. I didn't include it here, but you can get heat flux and temperature. So the collision integral basically doesn't do anything to mass here, because whatever goes in, ID1 particle with ID1 particle with ID2, they have the same IDs going out. But they can exchange momentum and energy. And yeah, what you get out of it is basically the flow of momentum and the flow of heat. Is that kind of okay? I mean, I know you're going into more detail later. You can bring it up if you want. Yeah. All right. Does anyone have an answer for this? You can be simple about it. I'm just trying to make a point.
I'm equilibrium anymore.
Okay. Good. Anything else? All right, so maybe I'll just put this first thing up here. Under what conditions would I have a compressible phase space if I started with, so the Boltzmann transport equation, no external force, I lop that off, I just have a collision integral. So the system is self-contained in principle. Yeah, I mean, yeah, I'm looking for a dumb answer. Okay. Approximate the collision integral as some kind of tendency for it to spread. So this P would now be like an F1. And if you plug this in, then you can write down an equation. So I'm now just transforming F1 into this P, probability density. And you get an equation describing how this probability spreads. So this is a Fokker-Planck equation. The key thing to note is that we're somehow including the fact that all these collisions combined are kind of smearing out our knowledge about where things are, because things are colliding. And so we've kind of captured it in this abstract way in terms of a diffusion coefficient. And this just gives us how much it tends to spread. So what I was going to do before I put up this slide was maybe mention stuff about Langevin equations, but there are almost too many things to deal with. But if you guys want me to talk about it later, I can come back.
So if you got rid of the force term, the shape of the distribution function can be changed, but only if you have dissipation, right? Not in the case. So if you got rid of the second term, then phase space.
Which second term?
The
one that I dropped off.
Yeah, if you got rid of that, then phase space would still be incompressible, right?
Oh, so you're right. I didn't directly answer the question. The point is that by approximating how our distribution changes in this way, we are in some sense losing information about what's happening. And so we've excluded explicitly the effect of all the ways in which any given particle can interact with other stuff. So when you do that, well, then your probability distribution will smear out. If you look at so let's say you go back to the Liouville equation. Well, in principle, you'd have all the information you'd ever need. But if you were to do this kind of operation, well, then you wouldn't be keeping track of, say, the n-1 other variables or whatever. You've kind of averaged over them. You take them into account implicitly, and the effect is that you get a kind of spreading in that space. You okay with that? Okay. All right, so this is, I'm just now listing methods that might fall into these categories. So basically I started off by listing methods, and it's a mess. There are like probably 100 ways to do it. But I'm just roughly grouping stuff that might fall under certain categories. So if you do Hamiltonian mechanics, then you can at some level work with the Liouville equation. So molecular dynamics, Monte Carlo, direct simulation Monte Carlo, I guess would kind of fall under that category. If you can define a full Hamiltonian for your system, then you could do these things in principle. Just leave that as an asterisk. Over here, if you somehow can get rid of a bunch of extra degrees of freedom, if there's a principal way to do that, then you can do something like lattice Boltzmann method. So that's basically taking the Boltzmann equations and moving stuff on a discrete lattice. So like ensemble Monte Carlo, which Ian does, is basically you take a particle and you move it, so you stream it forward. So P over M is V. So V dot the rate of change of F in space just tells you how much stuff is changing because it's streaming, it's flowing, advecting. And then you take into account some kind of collision interaction that you do stochastically. So you can tabulate it, you can pick from a number of possible collisions. And so it's basically stream, collide, stream, collide. Okay. Hydrodynamics, okay, so there are all these methods, and this is just a bunch of jargon. What I will say is that if you have a method, any simulation method that in principle could conserve mass, momentum, and energy locally in space, then you will pretty much get something that gives you the hydrodynamic equations on average. So all these methods kind of do that. Not necessarily dissipated particle dynamics, but I guess sometimes. The identities of these actual methods don't matter so much. I'm just saying that there are a bunch of them there, and there are many more I haven't listed. But I guess, does anyone else have anything else I've left out that's obvious? And I just feel like the one thing that's difficult to connect is, what these methods are actually simulating physically. So I just try to go back to the equations, just get a closer look at that. Okay, so now I can finally jump into hybrid methods. And I divided that up into two rough categories. So there are multi-physics models where you take something from here and combine it with something from here, say, between these categories. And then there are other methods that may just be molecular dynamics, but here everything is atomically detailed, here things are just blobs. So I'll probably look more at this. Okay, so going back to the scales, I had this really broad range, and the reason I'm doing this is, given what people have done in the past decade, you can have multi-scale methods that pretty much can do everything molecular mechanics can or continuum mechanics can. But I guess you have the extra cost of doing two things at once. But it's not, mesoscale methods aren't kind of in between. They actually just are anything that might have non-equilibrium behavior, which can happen pretty much anywhere here. So if it's not equilibrium enough and maybe too heterogeneous to bother simulating with one method or another, well, then you might want to take some two-pronged or multi-pronged approach. Okay, so one thing you might think of doing to do a multi-scale or multi-physics type method is to extend the range of applicability of continuum methods. And you can do the same with molecular mechanics. So I guess I'm going to talk about both. Whoops. I just wanted to say that, what did I want to say? All right, so I guess we're working from this direction now, and I'll try to remind you when I'm working from this direction. So let's just leave all this up here. And so you guys remember this. So there's some solute and there's some surrounding solvent. And one thing that you might think of doing is allowing the amount of solvent to change in the system. That seems like an obvious solution. The question is, can you do it? And there are a number of methods that try to do this by working with some adaptive boundary. So there are a bunch of them. But I'll talk about one specifically. But in general, there's always a question of whether or not you can actually delete or add stuff in a principled way. So can you add, so let's say you want to expand this gradually because you know your solute's growing. Well, how do you add a layer of solvent on the outside such that you are respecting equilibrium thermodynamics? That would be one question you might want to ask. Another question might be, can I add stuff on the outside such that I can actually respect the hydrodynamic flows that might be present in the system? So, point is, it's complicated, but I'll just show this one particular approach. So the basic idea is divide your Hamiltonian, so divide your interactions into spatially into a high resolution and a low resolution region. So let's call this high resolution. And then out here, we'll say there's some low resolution region and we're not actually representing it explicitly. So we have some notion of keeping track of solvent out here, but it's invisible. And what we want to do is allow this outside region to blend smoothly with the inside region. So if we expand into it, we don't all of a sudden perturb our system because we just added a bunch of extra atoms. Okay, so you do some kind of matching between the two boundaries. Details obviously matter. I won't go into them. But over this region where you kind of stitch the outside here, this imaginary region with the inside, you just transition in such a way that you recover or you respect whatever it is you're trying to preserve in your system. So if it's just equilibrium properties, well then you want to do some kind of transition such that you can actually recover them. You'd probably have to do different things in your stitching if you wanted to deal with hydrodynamics or something much more complicated. Okay, and then what you do is you just allow your solute to dictate how much of stuff you have around. Okay, and then, so now this boundary, which can fluctuate, is just now a new dynamical variable. Okay, so if you do that, here's a simulation from from this one particular method that came out recently, JCP. You guys see the solvent?
Mm-hmm.
So I think this is a pretty simple system. I think it's just Leonard-Jones interactions. This works for any potential in principle, but I'm sure it's difficult to do with water. You see it's pretty neat. And so basically you can minimize the amount of solvent that's actually needed to do the simulation. Okay, so that's one kind of hybrid approach. If you guys are curious about its performance, the details here don't matter, but if you look at the radius of gyration of that polymer and how often it's observed, you can do an explicit solvent, so a really big box, and just brute force it, and compare it to the method that I just showed. According to this, it's pretty good for a 30 segment chain. Okay, so the next question, I guess, this is my bias. Do we need hydrodynamics? So I'm convinced that the answer is yes, but maybe you guys aren't. All right, so the point I want to make is that hydrodynamics is probably relevant at shorter length scales than one would think. You say, okay, this length scale is on the order of nanometers. Is that a continuum? No. Okay, I'm not going to use it. But if you try to imagine what kinds of flows might actually be possible on that scale, then it still might admit of a description that's averaging over the particles rather than keeping track of all the explicit details. The key is keeping track of enough details so that way whatever microscopic interactions modulate the flow, those are captured and then you can get the flow to behave in the way that you expect. Okay, so this is just a depiction of basically a 2D domain, so it's a two-dimensional fluid, and I'm just showing 2D turbulence. So this is a simulation that I've done, and the only thing I guess you really need to look at here qualitatively is just the fact that it's swirly. But red regions are flowing fast, blue slow, and there's an awful lot of mixing going on. Maybe that's another thing to notice. So the reason why I use this simulation is just to motivate a connection with, say, how proteins and membranes might actually flow. So if you have some membrane lipid bilayer dividing some extracellular, intracellular fluid region, and if you look top down, you might wonder, how are these lipids going to move? And in this simulation, which is a coarse grain simulation, you can actually track where the lipids are going. And you can see that it's more of a swirly pattern. I mean, if I had guessed that these lipids might diffuse throughout the membrane, I may not anticipate that it would look swirly, like a soap bubble or a soap film. And so it looks kind of like this. So it suggests that maybe when we're talking many nanometers, maybe I don't know, micron, that maybe on that scale things do look like flows rather than just pure diffusion. All right, so one thing that you might try is to then just do a hybrid method where outside some region, let's just take into account the flows, and then we'll only resort to molecular dynamics wherever we need really high detail. So, and this is exaggerated. You obviously probably don't need this much solvent if you're simulating something this small. But what you can do is, bathe your solute in some solvent. You capture a lot of these structural details, like this, maybe hydrogen bond networks around it, blah, blah, blah. But then maybe you need a big enough domain for, I don't know, whatever reason, and you do need to capture some kind of effects of the solvent, but you don't need the details. You don't need the hydrogen bond network or whatever. Maybe you just need to capture, I don't know, fluid velocity. So you can imagine a bunch of these bubbles of whatever solute floating around, and they have bubbles of explicit solvent, and then they can flow because the outside region is treated as a continuum with some velocity, and they can merge and so on. So that's actually really hard to do, but it can be done.
Is there a reason you use a bubble, like in the one before where it had expanded outwards? Why didn't you go with more of like an oval shape since it was long and not wide?
That's a good question. So for that particular method, I forget what it's called. It's an adaptive boundary method. So that's Jason Wagner of J. Panda. So they and I guess it's Benoit Roux, and I'm trying to think of the stuff in Charm. Immersed. Someone help me out here. It doesn't matter. Anyways, you have some central location for your system, and for these methods where you ignore solvent on the outside but somehow include their average effect at the boundary, it's a lot simpler to think in terms of shells. And so, you basically be compensating for changes in free energy by adding shells. It's easy to do that way. But if you were to add it, asymmetrically, I guess it'd just be harder. But I mean, it can be done in principle. The implicit solvent methods are doing some kind of thermodynamic averaging. So I think it's particularly hard in those situations to do something other than a sphere. I mean, it could be done, I'm sure. In simulations like this, I guess this is a bubble too. We'll just come across it later. But you don't have to have a bubble. You don't ever have to, say everything about the system on the outside, just like those other methods. You don't have to treat it as a single number. You can actually do the simulation as if it were a fluid. In which case, it's keeping track of all the details for you. Okay, so the idea is in some subdomain you have MD. Everywhere else you have a continuum, and then you have some boundary conditions that you have to match at the interface. And so again, it's one of these lists. We don't have to go over details. I'll just leave it up for now.
How do you communicate the properties of a cell fluid near the particle region to the particle region again? So I have certain density or temperature of cell, and I want to have it couple that to the particle. How is that done?
I mean, are you asking something more specific than what I've already said?
Yeah.
Can you ask it again? I'm still confused.
So I have a particle region neighboring the continuum region.
Okay. Let me just bring it up.
How exactly do I couple the properties of the continuum region and the particle?
Yeah, so I might have a slide later on, but I can say a couple of things. Maybe it's actually best to draw. I don't know if I'll just erase this. Actually, let's say we have a big pipe. That goes off to infinity. It's coming in from wherever. So let's say this is our molecular region. So we have I don't know, whatever. Not to scale. Okay, it's not random enough. Okay, so let's say this is molecular. This is continuum. So how do you, whatever is happening over here, how do you transmit that information to this region? So how is it going to be captured? So we know since it's a continuum, it's going to have to be some kind of average, because that's what it is. You smooth over the details. That the average that you take can be, let's make some room here, can be something simple like, right, so in this region here, you have, well, I drew the waters a bit too big, but let's say you had enough waters in here that you can take some kind of average to get its density, right? You just get the average density. Well then, whatever the density happens to be here after some number of time steps, you could then use as the density that this fluid cell over here, this adjacent one, sees. And so whenever you do the calculation, it's as though you had a fluid cell, but you have to map it then to the fluid value. And you could do the reverse. So that's a little harder. How do you place a particle once you just have a fluid density? That's partly solved by that adaptive boundary method, right? So in order to make it bigger, you have to place stuff. So when I say you have to deal with boundary conditions, that's like a really difficult problem. And some of the methods overlap, and you can apply all sorts of techniques to do that. The other thing you might think of is, across this surface, count the number of waters that are moving across it in some given amount of time. And then you have, at this boundary, you have a flux. So as opposed to calculating a state variable, density, you can get the flux of the density across that surface. And that also works with fluid boundary conditions.
So you would have like a creation and destruction term that's included in the particle equation. That's like a Monte Carlo step that has and destroys particles, which you know the density.
Yeah, okay, actually that's an interesting point. So there are lots of different approaches. One that people do all the time because it's easy is, actually this seems like a really bad idea for this pipe flow problem, what I'm about to say. But let's just say I have a molecular region and some kind of boundary overlap region. Then what they do is just kind of trap the particles in this region with a soft potential. So everything in here, particles just feel the forces that they feel. Out here, there might be an increasingly steep potential, so that way it's going to kind of, so if I'm, there's some kind of, we'll call this little r. And so that's r, that's a little r. And you might actually have, something like that, I don't know. That might seem, seems kind of dubious, but if you kind of fade out the particles, so you have a van der Waals interaction, you can make it softer as you move out this way, and then allow the fluid to kind of take over the interactions throughout this entire region. And you can make this wider. That's, I don't know, it seems to work, but yeah, I think a more principled approach would be to do Monte Carlo. But then, you come across other difficulties. How do you, if you place a particle in there, then what's its velocity going to be, for instance?
Yeah, I was going to say, so what would be the distribution function for the little particle cell? Is there a question? Right?
That's a good question.
Maxwell Boltzmann, it's always Maxwell.
It'll probably be okay to just use Maxwellian if it's Navier-Stokes. If it's beyond Navier-Stokes, which I will touch on later, then maybe not. Maybe you need something else. All right. That's boring. Okay. So, here's not a spherical blob. So you have some solute, you have some solvent surrounding it that's explicitly represented, and then you have some fluid on the outside. And the nice thing about these simulations is you can just trim as much of the solvent as you want. So I keep putting this up every time I do a presentation related to this. And I don't really know of anyone who's done something like this detailed, where you can turn everything off on the order of a single cell, except in lattice Boltzmann simulation. So if you, instead of doing MD in here, did lattice Boltzmann method, then you could do lattice Boltzmann here, and then something a little bit cheaper, which is just like -6. And then you can actually switch each cell between continuum and then Boltzmann representation.
How far away do you have to get from the protein until the water has sort of bulk water statistics?
I don't know the answer to that question. But I can guess. I can guess just as well as you. Well, I mean, you definitely go out beyond the first solvation shell, but then also probably the second. If you have something that's highly charged, I don't know, you could probably do many angstroms, tens, maybe many nanometers. If you have also periodic boundary conditions, you might be able to get artifacts that penetrate way into the domain. So that, again, that adaptive boundary simulation I showed all of you, they tried to I think perturb stuff at the boundary in such a way that you would see it on the other end, and just see if you could mitigate that by actually adding in this kind of imaginary stuff on the outside, which is just a kind of a soft or coarse-grained version of the actual stuff on the inside.
What would be for bulk water to have some initial non-equilibrium state? How long would the relaxation time for the bulk equilibrium statistics be? Because you could conceivably put a boundary around the protein in an MD simulation of a guess, and then you can run it for microseconds or something, and then you can calculate the statistics outside of the boundary, and that would be a way of actually figuring this out, right?
Calculate the statistics outside of the boundary. I mean, I wouldn't know how to do that if your solute is changing shape so quickly. And then also depends on...
Sure, you have a non-equilibrium distribution within the boundary, but we're saying there's a point where you get far enough from it. Now the water behaves roughly like bulk water, right? So if the... Well,
here's a question I haven't answered. So let's say I'm just simulating water, but I don't have any ions. Then, let's just throw out a number. Let's say I can transition to continuum 6 angstroms away. That might be small, but let's say I can do that. If you add in ions, it may be the case that the charge is high enough that I can still model 6 angstroms out the density pretty effectively, but I may fail to capture some aspects of the energy flow. So it kind of depends on what you're looking at. Dipole relaxation is going to be faster probably than translational. It's, if you wanted to capture something that had to do with a residue changing charge, transferred somewhere else, or I don't know, then you might care about more detail, in which case you wouldn't transition to a continuum sooner. But this is problem dependent. I'm just shooting from the hip. Okay. All right. So so I'm talking about this fluid stuff, which seems feasible, or seems not too out there, but the question is, can you even do what I'm saying you can do? I mean, I suggested that people can, but does it even make sense? And the main problem, I think, is that, well, your fluid grid cells are basically on the order of only a few molecules, right? So if this is your fluid grid, and these are just some, maybe a monatomic gas or something, pick your favorite fluid, then say we're talking about something like on the order of water or argon. Then if I have nanometer-sized cells, the issue with that is that my fluctuations for any of the quantities I want to compute are going to grow inversely proportionally to the square root of the volume, 1 over the square root of the volume. So, so fluctuations are going to grow as I shrink my cell size. Also, when I take my averages, I'm taking them over presumably some period of time, because if I only have 1 in here, am I really going to take an average? I probably need some time window. Before I get here, it will also scale inversely proportionally to the square of the time step, say, for your simulation. Okay. So basically, once your spatial resolution is on the order of the mean free path, and the temporal resolution is on the order of the collision time, the mean collision time between your constituents, then what is supposed to happen, and I guess I can leave this slide, but what happens is you get this thing called the Knudsen number, which is a ratio of your mean free path to, say, spatial resolution. Well, that's basically on the order of a grid cell size. That's approaching unity. But normally when you do fluid simulations, Navier-Stokes is valid for when that's small. Knudsen number is very small. And so in order to deal with the situation, you have to do something other than Navier-Stokes if you want to capture a certain phenomena. Although I will say, as a side note, Navier-Stokes is pretty well. Okay, so in order to go top-down, we're going to talk about basically going from a fluid and allowing it to simulate something down at the nanoscale. So I'll just walk everyone through this, and then I'll go to something else interesting after the fluid stuff. So if I have some conserved quantity phi, then its rate of change plus the divergence of its flux, so the stuff flowing out, can only be equal to whatever is put into the cell or taken out of the cell. If nothing is put in or taken out explicitly, well, then the only way that quantity can change is if it flows across a boundary of that cell. If you had, like a drain, then of course you can take stuff out. Okay, so we've already seen these equations. If you are talking about your conserved quantity being mass, well, then you have mass continuity. You can do the same for momentum, energy. I'm leaving a few terms out just to illustrate the point. This includes stress. So this is shear, from shear flow. I can get into details later if you guys want. But the normal way to get actual Navier-Stokes, so this is not enough for Navier-Stokes. To get Navier-Stokes, you have the stress expressed as being proportional to velocity gradients. So this is Newton's law of viscosity, and when you plug it in here, you can rearrange stuff, and you get that form that I guess most of the engineers like to write it this way. And then, I continue writing, but you guys get the idea. So they write in terms of u, the velocity, that's a primitive variable, whereas rho times u, the momentum density, is a conserved variable. Okay, so this is Navier-Stokes, nothing super interesting. I could also include stuff for heat flux, but I didn't. I could put in Fourier's heat law. The key is to account for thermal fluctuations. So in order to do that, you can end up adding this stochastic term. So in this case, this S is a stochastic stress. So the stress tensor will have some value that's calculated from these velocity gradients. But you might say, well, since we're doing the averages on a short spatial scale, or a small spatial scale, short time scale, well, then we are also going to observe probably some deviations from that average, and we can account for that if we get the right statistics. We can account for it by putting it in as a stochastic term, and then now our equations have these fluctuating terms in it. Okay, so Landau and Lifshitz did this in a pretty principled way, and you can figure out what the variance of these terms will be. Okay, now part of the problem is you might say that does the stress itself, is it always proportional to this? Well, it can't be. That's some kind of average. There's some stochastic term, so that's implying that something else is changing it. If you remember back to when I had the Boltzmann transport equation, well, the thing that would be changing it would be probably collisions. So the collisions are all the things, it could be as complicated as you want. If it's many-body, then all the collisions are what's giving us our fluctuations in the stress. So in some sense, this is kind of capturing, or kind of, it's giving us back some account of all the things that we were neglecting before because we were oversimplifying with like a two-body approximation, per se. So this, if done right, you might think in principle could capture the global effect of the solvent, the mean effect of everything else surrounding something. Right? So all the many-body interactions, rather than just talking about pairwise collisions. I know that's kind of vague. Is that confusing? I see squinting. All right. Not the clearest explanation, but just if you guys want.
Just a lot of details.
Yeah. Okay. All right. So don't worry about why this is for now, because we'll go down a rabbit hole. But I'm just suggesting that, well, maybe these stress terms could be enough, but maybe not. Maybe actually these equations for mass, momentum, and energy, which remember came from taking moments, velocity moments of the Boltzmann equation. I have no reason why I had to stop at the second moment. So if I were to continue that expansion out to however many moments, an infinite number, then you might think, in principle, I can capture all the interactions I could have been modeling with a Hamiltonian, right? Just like in the BBGKY hierarchy. So there's always this question, well, where do I truncate the moments? And the one thing I'll point out, I guess, is that, well, if you truncate them too soon at the energy equation, well, then you're dealing with averaging when your window for averaging, your temporal window, is basically on the order of a collision time. So it seems like a bad way to at least do averages numerically, at the very least. If you go to higher moments, this one higher, it turns out you get terms that are expanded in the order of the collision time. And so you can see if this collision time is, let's say, very, very, very fast compared to what we can observe, well, then this is when you basically take the limit as that goes to 0. And you see that you just get, sigma is equal to this term. If you multiply it through by tau, that's gone when tau is 0. So you don't actually have this delay in how the stress relaxes. But if you do observe things, your d by dt is allowing you to observe things that are changing very rapidly, well, then you do need to take into account the delay. Okay, so the only point that this slide makes really is that, well, clearly the way in which we're taking averages and then stopping at these three equations is restricting us to some kind of average that gives us a notion of equilibrium in each cell. Things have relaxed in each cell, in each fluid cell, such that the average that we're taking is representative of the actual average. If that's not the case, if you don't have equilibrium in the cell, things are taking time to relax, well, then you might need extra equations. Okay. So I'm just going to put this out here. So if I were to count the number of equations, I end up moving from 5 to 10. So you can see that it gets more expensive. But if you try to imagine how I would simulate some kind of complicated shear flow at the nanoscale, so let's say a microfluidic device, there might be situations where this is actually appropriate. Moreover, if I'm actually doing the molecular simulation, but I want to stitch it together with continuum, then I probably shouldn't be using Navier-Stokes as my continuum model. So I should at least be using Landau-Lifshitz Navier-Stokes, which means it has the fluctuating terms at least. But I might actually want to include this. So the point I was making earlier is that it's hard to take these averages, but if you have a way to account for fluctuations, you may not need to be forcing yourself to take a thermodynamic average artificially when the cell doesn't admit of that kind of average in the first place. Okay. And then this is just for completeness. You can include heat flux. Okay. So here's just one simulation I've done of a lot of you guys have seen this. So this is fluctuating hydrodynamics on the right and Navier-Stokes on the left. And what I basically have is 5 nanometer width jet. Reynolds number is, I think, 1-ish, so pretty low. Not where you would expect to see turbulent-like behavior.
What's a Reynolds number?
Yeah, I'll write that down in a second.